following content is provided by MIT OpenCourseWare under a Creative Commons license. Additional information about our license and MIT OpenCourseWare in general is available at ocw.mit.edu.
Well, okay, this is my lecture on section 6.1 of the notes. Really the central problem of numerical linear algebra is solving AX equal B by elimination. That's what is used much more often than anything else. But we're talking about sparse matrices, large sparse matrices. That's what we have in mind for a long time now. They're probably all lectures coming up thinking of those matrices, and this is the prototype of a large sparse matrix. Okay, so the main point of the lecture is if you take the unknowns in whatever order they're given, here I took them numbering along the rows 1, 2, 3, 4, 5, 6, 7, 8, and so on. That's you got to stop and think or get the computer to look at reorderings, because the reorderings can make an enormous difference in the fill-in. So this is actually the key word for this lecture is, and the key concept is the fact that as elimination goes forward, a lot of these zeros become non-zeros. So let me see it happen first of all. So this is the whole idea of fill-in. What's going to be the very first entries that are filled in? Well, let's see. I guess that the very first row operation, if you took the matrix like this and did elimination, 4 is the first pivot. You would add 1/4 of the first row to the second row to make that a 0, right? And then what would happen? This would change that number. That's okay. But this would put a new number in there, right? So a new number would appear when we do that first row operation. And then also working with this pivot, I would operate on that row to make this a 0, and then this would change. That would fill in, right? And I guess that this already has something, so that won't be new. So each of those steps, each of those row operations filled in a non-zero and reduced the sparsity of the matrix. And the sparsity is what we're living by. So we want to know, and now if I continue and continue, we'd need MATLAB to use SPI in MATLAB to see what the picture would look like. It's very interesting to see it. SPI shows you the non-zeros. We're very much focused on what's 0 and what isn't 0 in matrix entries. We actually keep track of that, the structure of the matrix, as well, of course, as separately keeping track of the actual numbers. So one place we're keeping the actual numbers, but in the decisions on ordering, we're only interested in zeros and non-zeros. So let me look even more at this fill-in. Just now, you saw it happen up there. Let me just look at a single fill-in step. So I have a row J and a row I. And this is going to be the pivot that I'll use to eliminate this. But in this row, there's another non-zero. And in this row, the case entry is not non-zero. It's 0. So this is what we start with prior to elimination, just as we did there. I just want to focus on the small, on the fill-in occurring. Okay. So what does, of course, this isn't on the diagonal. This is in column, this is in column K, which is somewhere far out in that case, somewhere close by in that case. But we're seeing this is on the diagonal. That's the pivot, the jth pivot that I'm ready to use. So I subtract a multiple of that to remove that. So what does elimination will not change the pivot row. And it will produce a 0 there. That's the point. But then the real point that I'm making is that when I multiply this by the right number to produce a 0 and do the subtraction, this 0 disappears. That fills in. That's some A, I, K, new. The new value in row I, column K is not 0. Okay. So we see that as we saw it for numbers. Here we're seeing it symbolically. Let me see it graphically, because everybody sort of, to visualize the big picture, I think everybody finds the graph description of the non-zero structure the simplest to imagine. So the graph for this little problem would be, so what's the graph that tells me where the non-zeros are? Again, it doesn't tell me what numbers they are, just tells me where they are, which positions. It's only the positions that I worry about in deciding on the ordering to use. Then I execute using the actual numbers. But in deciding on the ordering, it's just the positions. Okay, so I think of my graph as having a node for every row. So that's node J for row J. This is node I for row I. And somewhere we'll have a node K. Okay. So at the start, so those are the nodes. What are the edges? Well, there is so the edges come from the non-zeros in the matrix. So there's an edge from J to K, because this is not 0. And there's an edge from I to J, or J to I. I'm not worrying about the direction. This is not a directed graph right now. So this is the start. But there's no edge here initially, because AIK is 0. And now in this graph world, well, it's so small we can just focus on the part that's going to change a little. The rest of all the other rows have their nodes, and all the other non-zero entries have their edges. So this is a tiny part of the big graph. But what happens to this tiny part? Okay, so again, I want to see the same elimination step, just this way in the graph world. Okay, so after what edges are there? So again, it's J, I, and K. And after I do elimination, well, J is still connected to K. That's still there, no change. J is no longer connected to I, because elimination killed that edge. But elimination created a new edge, I to K. So that's essentially what elimination does. Maybe we can say it in words. When this edge disappears, at the same time we create new edges but connecting any two nodes that were both connected to J. You see that point? If I'm using J as the pivot row, then I look on that row and say, what non-zeros are there? What edges are connected to J? And I see one. And then when I do elimination, I'm going to introduce, exactly as happened here, a new edge between any pair that were both connected to J. So we're kind of fighting against creeping fill-in. And the question is, what order should we do these eliminations? So now think of a larger graph. Actually, I guess we could somehow think of that. I guess maybe we could try to visualize it, but maybe not succeed. So the graph for this, for that problem, Well, could that serve as the graph? I guess it could, really. Well, I would remove, I'd whiz away if I'm given the values on the outer edges, then I would remove all those. But essentially, this is the graph for that matrix, right? Well, yeah. If I number each of the nodes 1 to 16, and I would do the numbering the way I did to produce that matrix. Now, the whole question is, if I do some different numbering, that'll shift around. That'll just be a permutation matrix, right? If I do a different numbering, so matrix-wise, I have my matrix K2D. What happens matrix-wise for if I do a numbering, a different numbering, a reordering? That just permutes the unknowns and the equations. So really what happens is some permutation multiplies K2D on the left, and its transpose does the same thing to the columns on the right, because this permutation will change the order of the equations. This permutation will reorder the columns to come back, to bring the diagonal back onto the diagonal, but in a different order. Well, we won't know it with all those 4s, but that will have, again, all the 4s on the diagonal, but the -1s are moved around. Of course, none have disappeared or been created by that. It's just, that's giving us a new order. And so that's the reordering matrix-wise. What's the reordering graph-wise? Graph-wise would be, instead of this numbering of unknowns, 1, 2, 3, 4, 5, 6, 7, 8, and so on, 9, 10, 11, 12, 13, 14, 15, 16, we have a different order, different numbering. So the computations, the computer science aspect, you could say, is not going to be difficult. Actually, we should think, and maybe we'll think in a minute, from the computer science aspect, the actual execution, I'm certainly not going to write out a permutation matrix. That's ridiculous. I'm not going to draw a graph and keep that. I'll keep some list of positions for non-zeros. So we'll say a word about that list later. But here I'm trying to say, how do we get an idea of what the effective reordering is and what a good reordering would be? So here, this is a specific reordering that I want to mention right away because it's so straightforward. You can get the idea of the red-black ordering without any big computation. This is fundamentally the winner. This is what people use all the time. And MATLAB's / is going to have that available. Inside this, the codes that are called are the column or symmetric matrix approximate minimum degree. So that's what this AMD means, approximate minimum degree. So that's the basic idea that I'll come back to as soon as I've just drawn the red-black picture. And then it's so important that people don't stop thinking. And then, so another sort of high-level picture of how to do an ordering is look for graph separators. That's become a big step in the world of computational graph theory. And that leads to something called nested dissection, which is separators of separators of separators. The usual keep going with the same idea that you see in algorithms. Okay, what about red-black? Red-black, I'm simply going to, imagine that this is a checkerboard. Well, it's the nodes that I'm looking at, not the squares. So imagine, so that's red, black, red, black. So I'm going to number first, I'm going to take all the reds first. So that I'm changing this numbering now to take all the reds, 1, 2, 3, 4, 5, 6, 7, 8, and now all the blacks, 9, 10, 11, 12, and so on. I'll stop there so your eye will know how to fill in. What's the point of that? If I take a red node and look, suppose this first one is a red node as it is. Okay, then what do I know about the positions of those -1s, the non-zeros in the matrix? They're associated with black nodes, right? The neighbors of this node number 1 are black. The black ones have numbers from 9 to 16. So the black, well, everybody sees it. That with this molecule that has a 4 in the center and -1s beside it, those -1s are associated with nodes of the opposite color. And that's what we see here in the actual numbering. So what does the matrix become? What does this, if I do that permutation, the permutation that's associated with that renumbering, what will the same matrix, well, here's the same matrix, but now I'm permuting it, and so what does it look like? Maybe I can draw it smaller. I think I probably can. So in this pretty special situation, where the red nodes are not connected to any other red nodes, only to themselves, I think I'll only see the 4i. This is red to red. Those are the 8 red nodes. It's an 8 by 8 identity matrix times 4. And the blacks are only connected to the black. And all the -1s are connections between red and black. That is, this far off the diagonal, what shall I call it? B, I'll just pick a letter, B, and B transpose probably, because I know the matrix is going to stay symmetric. If it started symmetric, as it did, then this operation of reordering rows and columns compatibly is going to leave it symmetric, and it must look something like this. Okay, is that matrix more sparse than before? No. It's got the same -1s. They're just all pushed up into this corner. Will it have some fill-in as we go forward? What's the answer on that one? As I go forward, maybe I haven't really thought that through. My instinct is, yes, we'll have fill-in. Will we have more fill-in or less fill-in than the row by row ordering? I should know the answer. I think I'd probably ask the machine to tell me. My guess is probably not more. And we can, well, why do I think probably this is better? And of course, I should know exactly. In general, it's better to put off the evil day here. That is, this goes through the first half of elimination. I mean, you know what I'm thinking here. All the off diagonals have been sort of pushed down in the matrix. So that, let me do an example that shows why that's good. Suppose my matrix has a non-zero diagonal. And by the way, the first step in the good codes for elimination do a permutation exactly to produce a non-zero diagonal. So you're okay to start. You know where you are. Now, suppose that the non-zeros all show up, and I'll make the matrix symmetric. So that's the non-zero pattern. And my point is that's a very good non-zero pattern. Why is it good? It's good because there's no fill-in whatever. When I subtract some multiple, when I go to make this 0 to eliminate it, I subtract a multiple using the first pivot. It changes that, but it doesn't fill in anything new. All the only operations required are operating on the last row, which is already full. So there's an example in which the bandwidth, see, normally the bandwidth is like a good guide, but that's only for like pretty full bands. Here's a matrix that's not banded really. Its bandwidth is the full 5. I have to go out 5 columns until I get the last, until I get the non-zeros. So that has a big bandwidth. So bandwidth W, the bandwidth W is large, but it's the perfect ordering, but no fill. I don't fill anything. You realize that for banded matrix, we won't have fill in outside the band. Our concern is for fill in inside the band. And here we don't have any, because the bad row, and actually it often happens in some least squares and other problems that you might, this isn't quite as stupid a matrix as you might think. These might be blocks rather than single entries. You often want to think block-wise about a matrix. And when would you might think, why would you have a matrix that was well separated with block diagonal, which is really good, and then a few rows that are full? That seems sort of unlikely, but I guess I want to say it isn't. If you had a problem in least squares minimizing some expression involving that matrix, the block diagonal part, but with a constraint that maybe the sum of all the unknowns has to be 1, then when you use a Lagrange multiplier to bring that constraint into the problem, into the matrix, that's going to show like that. And the beauty of the Lagrange multiplier device is that also that it'll produce a symmetric column there. Well, we'll see that in the third part of the course. But my point is that this example is not as artificial as it seems. Okay, now, suppose we had taken the bandwidth as our metric, as our goal, or reducing the bandwidth as our goal, we would have made a bad mistake. Because if I want to do a permutation that reduces the bandwidth, I better put this up in the middle somewhere. So this is, that bad row comes up in the middle, and then I guess that these are maybe whatever. Well, I guess I need 3 x's down here. And I'm going to do the same permutation from the right, so that will move this column over to the middle. So this would be a reordered, this would be a P matrix P transpose thing, I think. And it's got a better bandwidth, right? Now we're totally confident of all these zeros here. But it will fill in. Where will we get fill in that matrix? So as we start, we're using elimination to remove those entries, no problem, because that upper left corner is the way the whole matrix was, no fill in up to there. But just as soon as we reach this one as our pivot row and use it to subtract multiples to knock out those, When I make those 0 by using that pivot, it's going to bring the whole, this will be gone at that time, but this will be non-zero, and that will produce new edges in the graph. Might be fun to look at the graph that is associated with this matrix and its permutations. But anyway, you see that this will all fill in. Okay. So again, in that small problem, we could really see what was happening. In the big problem, we can almost see it when we take a very specific, highly structured permutation like red-black. Although I haven't pinned down exactly what the count is like now. I'd be glad if somebody would just run a computer experiment, count non-zeros, count. So what's the good thing to count? How do you see what the fill-in finally was when you've done an elimination? Well, I guess that the L and U factors, which is what elimination produces, that's where the fill-in will be. So maybe I just make that point so that you could make these experiments that I have in mind and tell me what I ought to know about it. So if I have the matrix K, whichever it is, whether it's this one or any other, then the effect of elimination is to factor it into a lower times an upper triangular matrix. And I'll just mention the special case while I'm special positive definite case. We can adjust it so that K is L times L transpose. This is called Cholesky. We can arrange well, it will happen. We can arrange the scaling so that by putting a square root of pivots with L and the other square root with L transpose. So Cholesky is a MATLAB command, CHOL, and actually MATLAB, if you give MATLAB a symmetric matrix, or if you give MATLAB a matrix to work with, it will first ask, is it symmetric? If it is symmetric, it will hope that it's positive definite. So it will begin Cholesky. It will begin to look for this. It will begin the factorization, which is perfect for positive definite ones, until it succeeds and finishes Cholesky, or until it discovers that, nope, a negative pivot appeared, which signals that the matrix is not and was not originally positive definite, and then MATLAB has to accept, okay, now I may have to do row exchanges, pivoting operations, and all the rest. So MATLAB's sort of optimistic until on a symmetric matrix until it is told otherwise. But not all matrices are symmetric, so this would be the general case, almost the general case. I haven't included here the pivoting, the row exchanges that MATLAB does as it executes elimination. But let me just finish my sentence on L and U. L will have the fill-in in it. L will tell us, and U will, certainly. I mean, they both will. U will have these, that guy is going to be part of U. And this one is, I expect to see something there in L. So L and U will actually exhibit the fill-in so that you could find out how much fill-in there is simply by counting the non-zeros in the matrices L and U. This is to encourage you, because this is really a pretty experimental subject. Nobody, the best methods, or the favorite method, I think nobody can say best probably, but this approximate minimum degree, the favorite method, we could prove some theorems to show that it was better than something else. But to really see, is it successful or not on a wide variety of problems, that's really experiment. Just try it. Okay, now, what does it mean? So I looked at that specific one. Now I'm ready to look at the approximate minimum degree. And I'll contrast it with the perfect minimum degree. And there are codes for that, and those A's become M's. But it turns out, and I don't know exactly why it's the case, that the approximate minimum degree usually, if anything, it's superior. So these are the ones to use. So what does minimum degree mean? Minimum degree means, if I took this problem, I should draw the graph for that, for this matrix. So what does the graph look like for this matrix? I've got 6 nodes. So let me put 6 nodes in. Well, let me put 5, and the node in the middle will be the one that they're all connected to. So these in this ordering, those would be 1, 2, 3, 4, 5, and 6, and all the connections go into 6. So that's the graph for that matrix. And the graph for this one, so you probably see it better than I do. Well, what I had originally there, I guess this is the graph with the numbering 1, 2, 3, 4, 5, 6. This, what was there before the fill-in happened, the graph would look the same, but the nodes would have a different numbering, right? 1, 2, 3, 4, 5, 6. And then, so shall I just put the bad guy here, 1, 2, 3, 4, 5, 6? And then what's the point? That as soon as I use number 3 to eliminate 4, well, 3 was connected to 5, so a new edge is going to appear there. And 3 was connected to 6. 3 is connected to 4. When I use it, a new 4, 6 is going to appear. So those are a couple of the fill-ins. Those are the 2 fill-ins in row 4. Then when I go on to row 5, well, I'll fill in there. Those are the 3 below the diagonal and above the diagonal non-zeros that come from the bad ordering. I think. I didn't prepare that, but I hope it's right. Yeah. Okay. Now, so what's minimum degree? Minimum degree is simply sort of a greedy type algorithm, because we have no way to look far, far ahead and see what non-zeros are coming way, way down the line. So let's just take it where we are. We have to choose what should be the next pivot. So here, maybe let's say we take that first pivot. Good. It's all the. So what are the degrees of these? Let me redraw the graph before the fill-in. 1, 2, 3, 4, 5, 6. So I've got 6 nodes. That has degree 1. It's connected only to one other node. Actually, all these have degree 1, and this one has degree 5. 5 edges are going out of it. So the whole point of minimum degree is don't pick that one. Pick at each step, create the new graph. The graph expresses a fill-in, and we're not going to be able to avoid some fill-in normally. But at every point, take the graph as it is and choose as the next node to work on. That means the next row to use in elimination, the next pivot to choose. Choose one that has smallest degree. Don't choose this one. So that for this very special case, we have 5 choices for what comes first. We make a choice like that one. We do elimination. In this case, it doesn't fill in anything. Now I'm looking at the rest of the graph. I have 4 nodes there with degree only 1, and a node there with high degree, so I don't choose that. So I choose 2, and so on. So of course, minimum degree, approximate, or perfect, or any dumb idea is going to create the right ordering that produces this matrix. Okay, so, but I hope you've seen what minimum degree is. At every stage, you look down the column, just as here. Well, actually, what would minimum degree give here? I would love to have a complete picture. I think we could at least see at the start. Let me erase this red-black ordering and prepare to write in a minimum degree ordering. If I can recomplete that graph. Okay, so what node do I take first? Remember, the graph really does not have these pieces. I might as well erase them now. Shall I just erase? These are pieces that connect to known values that are on the right-hand side. So I think the graph doesn't have those connections, It's going to look pretty much as it did before. But I think now we have the graph of actual 16, the graph that we should be looking at. That's the graph of our matrix, the graph of the non-zero structure in the matrix. Okay, so what do you take as the first node? You take the corners, right. The corners are going to win because they have degree 2. These guys have degree 3. There's a degree 2, so I might take that. Or, well, let's see. What happens when I take this one? Then I have to see, okay, when I use that as the pivot, exactly what I did here, what's going to fill in? Well, I guess explicitly I know that two new edges fill in, and what are they? Well, maybe they're the same. I guess they are. This is edge number, so on the graph, it's probably easier to see than in the matrix. So I use this guy. By elimination, I'm removing the connections, so it maybe sits there as surviving to remind me which node was numbered 1. But these connections have been removed by elimination. That entry became a 0, and that entry became a 0. But there was a fill-in here, right? Okay. That's the first step of minimum degree. The second step, as you say, I'm going to do all the corners first, right? Because that has degree 2, and these still have degree 3. No improvement. It's kind of fun to do these. 2, and that filled in. Number 3, and that filled in. Number 4, and that filled in. Okay, what next? Well, there are going to be a bunch of choices now. And as far as I know, I could be wrong, I don't know I don't know what the choice decision, how the decision is made when there is a choice, when I have 1, 2, 3, 4, 5, 6, 7, 8 nodes, all with degree 3. But let me just take this one. So I'll take this as the next one, as number 5, I guess. That'll be number 5. That will kill all those connections and just leave the node, but it will put in that one. Any others? Maybe only that one? Did I do that right? Yep. I mean, it would have put in this one because those are both connected to this, but that edge is already in there, so nothing new. Okay, so actually, here I've created a node with that's also degree 3. So I'm going to have a lot of degree 3s here. But then after a while, I think when I get into the center, I'm guessing that the degree will go up. I don't think I get away with degree 3 all the way until the finish. I don't think. Anyway, you see the point that there are choices to make among equal nodes with equal degree, and then there's this calculation to make. Maybe I should. This is a moment to just mention, if I can do it, how you might organize this pass through. So this pass through the matrix is really just a pass through the graph. It's not looking at the actual numbers. It's just choosing the ordering, and then the next pass through, we follow that ordering with the numbers, finding the multipliers that go into L and the numbers that are left in the matrix U. Okay, so how would anybody reasonably write down the original list? So I have the nodes numbers 1, 2, 3, 4 up to 16. Those are the node numbers. And now with node 1, I'll list all the, so this corresponds to row 1 of the matrix. So I list all the nodes that are connected to row 1, to node 1. Well, node 1 itself is, I don't know whether to put that in or not. Maybe I will, and number 2 is connected to it, and number 5 above it. I'm taking the original row ordering. Okay. And then when I look at node 2, so it's just going to be a long list, but I'll have to have a break there to tell me that these numbers were associated with row 1. Now I want to know those associated with row 2. So row 2 had the connection back to 1. So this little group is going to be all the things connected to row 2. Remember, sorry, since I've erased all those connections, but you remember them. 2 was connected to 1. It's connected forward to 3, and above it to probably 6. Maybe that's 1, 3, and 6. And then a slash, and then whatever, node 3. So I guess I need one more line there to tell me I need a pointer. I need a line of a pointer that tells me, okay, number 1, start with the first one, 1, 2, 3. Number 2, start with the fourth one. Number 3, start with the seventh one. So that number 7 is pointing to the beginning of the sublist, the beginning of the short list that's associated to each separate node. Okay, and I guess what I'm saying is that this is a pretty compact description of the graph. This will tell me all the edges in the graph, because it tells me what 2 is connected to, and this tells me where that little set lies. And now if I, as I will, change the ordering, then I just reorganize the pointers. I'm going to speak roughly and not the details. Just in general, in the large, you could imagine that this is a pretty convenient structure to use for keeping the record of what the node numbering is. Okay, so that's, and the command NNZ is a useful one. That's a MATLAB command that counts the number of non-zeros. So N, and Z suggest exactly what that will do. So if you pick an ordering, like approximate minimum degree, and you pick a matrix, like this one, and you run Well, I'd be very interested in that. What if you run, you take the matrix, K2D, you take the permutation that comes from approximate minimum degree, that gives you this reordered matrix, which you then factor into, you then do elimination, which factors it in L times U, or probably L times L transpose because it's positive definite. And then I would do an NZ of L as a measure of fill-in. That would count the fill-in in L. And with symmetry, it would be the same in U. And if you have a better idea than approximate minimum degree, that's a measure to try it, to use as the criterion. Okay, just a little time to speak finally about this idea of graph separators. So again, I have to get back to a graph. Let me draw a graph under. So now I'm ready for this one. I'll put a little star next to it to say that it didn't look for a long time as if it could compete with number 2. But, because it'll be a different ordering. You could, in a way, it's going to be a block minimum degree ordering. Let me say what it is. And as I draw the graph, let me say when it might win. It might win when the size goes way up, 3D. In 2D, minimum degree is, on sparse matrices, is quite successful. So in 2 dimensions, until the size really gets big, that's going to be fine. In 3 dimensions, well, I'm still going to draw only 2, but in 3 dimensions or very, very large matrices, I want to think about this graph separator. So I'll make it, just so I really separate it perfectly, let me make the number so when you look at that graph, you might say, if I look at that set of nodes, so a separator is a set of nodes that separates the rest of the nodes into 2 groups. So I have a group of nodes P, a group of nodes Q, and no connections between P and Q. P is this part. Q is a similar part over there. S, the separator, is the part with the connection. So P is connected to Q only through S. So now if I think of ordering, in what order should I take the P, the Q, and the S? Well, our absolute rule is everything's connected to S, put it last. So you see that this is the block form of my small example here. Well, I didn't particularly have a P or a Q, but I certainly wanted to put S last. Oh, well, maybe I did. So maybe the separator here was, so what's the separator? Well, one possible separator would be like that, as S. P for these 2 nodes, Q for these 3 nodes. And the rule would be, I haven't said what I'll do within P or within Q or within S, but the rule would be put Q last. And of course, that was exactly the right thing to do. And we're following the same rule, just blockwise. So we have the block. So our matrix, what does our matrix look like when you choose this ordering? Well, you have whatever P is, the block of all these P's. You have the block of all these Q's, which might be connected to each other and are, but not to P. So the main point is to have these 0 blocks. And then everything is connected to S, and S is connected to itself. So it's all you've achieved, but it could be considerable, is to take an ordering in which P was, since P is not connected to Q, that produced these large 0 blocks. And, of course, they'll stay 0 as elimination goes forward. Those zeros there I don't have to do any pivoting operations, any row operations to make those 0. They're already 0. And so the only operations will be P onto S, Q onto S, S onto itself. And in many problems, it's the S onto itself part. So what will happen then when I do elimination on this? When I do elimination, well, I'll have whatever work is necessary within P. So I'll be factoring. Can I call that P, that part of the matrix? It's an abuse of notation. And this is the connections of S to P. This is the connections of S to Q, S to itself, Q to S, P to S, probably symmetric. But so when I do elimination, if I accept this ordering, if I accept this ordering and just go for it, elimination will factor P into LU, because it'll work up in the corner as it always does. Then there's no connection here, so it'll factor Q into its own LU. And of course, all this stuff down here will change. But effectively, these will become zeros, because then there's a serious elimination. P onto S will make that 0. Q onto S, Q will make that 0. This will be some, I'll call it SSS. It's some much fuller matrix block, smaller though, hopefully smaller, and but pretty full. So actually, in the graph separator nested dissection world, often most of the time is spent on that third block, just working with it, because it's the one that's pretty full. Okay, so how do graph separators work? First of all, you need an algorithm that finds a separator. And a lot of computer science attention has gone onto that. Given a graph, cut it in half. Find by a short, we don't want more nodes in the separator than necessary, because the work is going to end up there. So we want to cut the graph pretty nearly in half by a short separator. And then, so that's if we only did the algorithm, did the separation, the cut, the dissection once, that's what we need. But this idea of nested dissection, oh, you know what's going to come before I say it. The idea of nested dissection will be, take this, take the graph. Can I just draw it this way without drawing all the edges? Cut it by a separator S1. That gives a P1 and a Q1. But now what's coming? You're going to separate P1. In order to do the work up in that left corner for the P matrix, that's itself a sparse matrix. So now I'll look for a separator. And what separator will I choose for the left side of this graph? I'll choose the horizontal separator. This will be the second separator. It'll separate the 2 bits of P. The third separator will separate the 2 bits of Q. Now I have this part to work on. A fourth separator will, you see it's nested. These separators become nested. There's S5, there's S6, and so on. Okay, I think everybody sees in principle what nested dissection should do, and the question is, how does it compare with minimum degree? You see, it's just like a different, we're off on a different route here. And you can compute asymptotically for large N what power of N appears there, what power of N appears in minimum degree, but I would love to know, I would be happy if somebody used approximate minimum degree on our model problem and maybe also on some other problem. And we could see what power of N. That's essentially what we're looking for. So it's N to what power for fill-in and for the operation count, which the number of flops, which controls the cost and the time. Yeah. So it's what power of n appears there and what power appears in any other method. So there you have it for direct elimination methods. And I'll just mention the name of the guy. He's at University of Florida. And he's the one who contributed the code that MathWorks uses and has just announced a book coming on this exact topic to come later this year from Siam. So there will be a book that from the person I take to be the leader in this algorithmic development. Okay, and just to remind you, Friday is my guest, former PhD student, who's going to speak about numerical methods for finance, Black-Scholes equations and other problems to find the value of financial derivatives. Okay, see you Friday.